Water is essential for all known forms of life, and understanding how it came to exist on Earth is one of science's most fascinating questions. For decades, scientists believed they had the answer. Earth's water arrived via icy comets and asteroids during the planet's early formation stages. These objects, originating from the colder outer regions of the solar system, were thought to have collided with our young planet, delivering their icy cargo and gradually forming the vast oceans we see today. The reasoning behind this hypothesis lies in the unique molecular fingerprint of water. Specifically, the ratio of deuterium, a heavier isotope of hydrogen, to regular hydrogen in water provides crucial clues about its origin. Water with higher deuterium levels tends to form in colder, more distant regions of the solar system. Remarkably, the deuterium levels in Earth's water matched those found in a specific group of comets known as Jupiter family comets, reinforcing the idea that these celestial objects played a major role in delivering water to Earth. For years, this theory held strong, providing a compelling explanation for Earth's liquid reservoirs. However, as science often does, new discoveries began to challenge this seemingly well-established narrative, setting the stage for one of the most intriguing debates in planetary science. What if the story isn't as simple as we once believed? What if the water's journey to Earth is far more complex than icy comets alone? Stay with us as we uncover the twists and turns in this fascinating investigation. In 2014, the European Space Agency's Rosetta mission embarked on a groundbreaking journey to unravel the mysteries of comets. It became the first spacecraft to orbit and study a comet up close, targeting the enigmatic 67P/Churyumov-Gerasimenko, or simply 67P. Scientists were eager to confirm long-held beliefs about comets' role in shaping Earth's history, particularly their contribution to our planet's water. At first, the mission seemed poised to validate the idea. Previous observations of Jupiter family comets had shown deuterium to hydrogen ratios similar to Earth's oceans. Rosetta was equipped to take precise measurements of 67 ps water vapor, expected to align with these findings. However, the results were anything but ordinary. To the astonishment of scientists, 67 ps water vapor contained nearly 3 times more deuterium than Earth's oceans. For every 6,420 hydrogen atoms in our planet's water, there's roughly 1 deuterium atom. In 67 ps water, that ratio was far higher, creating a stark and undeniable mismatch. This discovery sent shockwaves through the scientific community. How could this be? If comets like 67P carried water so chemically distinct from Earth's, then how could they have been the primary source of our oceans? Suddenly, the once solid hypothesis was under scrutiny, forcing researchers to question what they thought they knew about our planet's history. It was a big surprise and made us rethink everything, said Kathleen Mant, a planetary scientist at NASA's Goddard Space Flight Center. The revelation left a gaping hole in the narrative. If not comets like 67P, then where did Earth's water come from? And was the role of comets in delivering water completely overstated? But science thrives on challenges, and as researchers began to revisit these unexpected results, they noticed something intriguing. Could there be an overlooked factor that distorted the measurements taken by Rosetta? The clues were there, waiting to be unraveled. The question remained, what if the measurements weren't telling the whole story? Let's dive deeper into this cosmic puzzle in the next chapter. The surprising results from the Rosetta mission left scientists scrambling for answers. Could there be a fundamental flaw in the long-standing theory of cometary water delivery? Or was something else at play? Determined to make sense of the anomaly, planetary scientist Kathleen Mant and her team embarked on a meticulous reevaluation of Rosetta's data. What they uncovered would open a new chapter in our understanding of cometary science. Mant's team proposed a bold new hypothesis: the elevated deuterium levels observed in 67 ps water vapor might not represent the comet's true composition. Instead, the culprit could be an unexpected interference, the comet's own dust. Here's how it works. As a comet approaches the Sun, its icy surface warms up, releasing both gas and tiny particles of dust into space. This process creates the iconic glowing coma and vapor trail we associate with comets. But it turns out that water molecules with deuterium adhere more readily to dust grains than regular water does. When ice clinging to these dust particles sublimates, transforming directly from solid to vapor, it enriches the surrounding gas with deuterium-rich water. To an observer, this skewed the readings, making it seem as though the comet's water had far higher levels of deuterium than it actually did. To test this hypothesis, Mant's team combined laboratory simulations with comet observations. They demonstrated how the interaction between dust and water molecules could create precisely the kind of discrepancy seen in Rosetta's data. So, I was just curious if we could find evidence for that happening at 67P, Mant explained. The results were striking. This phenomenon was not only plausible but likely occurring right under their noses. This breakthrough redefined the way scientists think about comets and their role in the solar system. If 67P's deuterium levels were skewed by dust, then previous assumptions about Jupiter family comets might still hold water, literally. It reopened the door to the idea that these icy bodies could have been key contributors to Earth's oceans after all. But the discovery also raised larger questions. How many other cometary observations had been influenced by similar distortions? And could this newfound understanding shift the broader narrative of how water, and perhaps life, travels across the cosmos? As science often does, one answer led to new mysteries. If comets still hold the secret to Earth's water, what does this mean for the search for water and life beyond our planet? In the next part, we'll explore how this discovery ties into the grander cosmic story. The revelation that dust could skew the deuterium readings of cometary water wasn't just a small adjustment to existing theories, it had profound implications for our understanding of the early solar system and the mechanisms that delivered life's most essential ingredient to Earth. If Jupiter family comets like 67P were once again contenders in the story of Earth's oceans, what could this mean for our broader understanding of planetary formation and habitability? Let's delve deeper into the significance of this discovery. A new framework for understanding cometary water. Comets have long been considered time capsules from the solar system's infancy, preserving clues about its formation some 4.6 billion years ago. They are composed of primordial material, including water, that formed in the cold, outer regions of the solar nebula. This makes them invaluable tools for tracing the origins of Earth's water. The rediscovery of their potential role in delivering water hinges on one key factor: the interplay between gas and dust. In the early solar system, icy bodies like comets and asteroids acted as reservoirs for volatile compounds, including water. As these bodies collided with the young Earth, they brought not just water but also organic molecules and other life-enabling substances. Mant's team's findings regarding 67P suggest that we may have underestimated the accuracy of previous measurements of cometary water. If dust-induced distortions were responsible for the elevated deuterium levels observed in 67P, then other measurements taken from similar comets could have been more accurate than we thought. This means that comets may still align with Earth's deuterium-to-hydrogen ratio, reaffirming their role as significant contributors to our planet's water supply. Asteroids versus comets, a collaborative effort? While comets have traditionally been seen as the primary culprits for delivering water to Earth, the hypothesis faced competition from studies of carbonaceous chondrite asteroids. These asteroids, originating closer to the Sun, contain water with deuterium levels that match Earth's even more precisely than some comets. This led to a growing consensus that asteroids, not comets, were the main contributors to Earth's oceans. However, the new findings suggest a more nuanced picture. Perhaps Earth's water wasn't delivered by a single type of celestial body but rather by a combination of sources. Comets, with their icy composition, and asteroids, with their rocky cores, could have worked in tandem to create the vast reservoirs of water we now see on Earth. This dual origin theory reflects the complexity of the early solar system, where multiple processes likely intersected to shape the habitable environment we inhabit today. Cosmic water, implications beyond Earth. The implications of this research extend far beyond our own planet. Water is a universal solvent, essential for life as we know it, and understanding its origins on Earth provides a blueprint for exploring its presence elsewhere. the study of comets gives us insights not only into our past but also into the potential for habitability on other worlds. For example, Jupiter family comets and similar icy bodies are thought to have delivered water and organic molecules to other planets and moons throughout the solar system. This raises the tantalizing possibility that the same mechanisms that brought water to Earth could have seeded oceans on Mars, Europa, or Enceladus. These celestial bodies are now prime targets in the search for extraterrestrial life, and studying their water sources could unlock critical clues about the potential for life beyond Earth. Rewriting the narrative of planetary evolution. Man's work doesn't just adjust a single hypothesis, it fundamentally changes how we approach the study of planetary systems. By identifying how dust influences the readings of cometary water, scientists now have a more accurate method for studying these icy travelers. Future missions, equipped with this knowledge, will be better prepared to analyze the true composition of comets, asteroids, and other bodies in our solar system. Moreover, this research reinforces the importance of re-examining data in light of new discoveries. The findings about 67P highlight how our understanding of the cosmos is a dynamic process, where even the most surprising results can lead to groundbreaking insights. The bigger picture, a shared cosmic story. In the end, the story of Earth's water isn't just about comets or asteroids. It's about how countless celestial processes, from the gravitational pull of Jupiter to the icy dust grains of a distant comet, converge to create the conditions for life. It's a story of cosmic interconnectedness, where every molecule of water on Earth carries the fingerprint of a journey that began billions of years ago. But one question lingers: if water was delivered to Earth by such mechanisms, how many other planets out there have undergone a similar process? Could there be countless worlds scattered across the galaxy, rich with water and teeming with life? The rediscovery of comets' potential role in delivering water to Earth is a step toward answering these profound questions. In the next part, we'll explore how this discovery shapes the future of space exploration and humanity's quest to uncover the secrets of our universe. Stay with us as we look forward to the next chapter in this incredible journey. This rediscovery of comets' role in Earth's water story opens exciting possibilities for future research. Upcoming missions, like NASA's Comet Interceptor, aim to study pristine comets to refine our understanding of their composition. Advanced techniques will minimize interference from dust, providing clearer insights into their molecular makeup. These findings also fuel the search for water and life beyond Earth. From Europa's icy oceans to Mars's ancient riverbeds, understanding how water moves through the cosmos could unlock the mysteries of habitability. Each discovery brings us closer to answering the age-old question: are we alone in the universe? Let us know your thoughts in the comments, and don't forget to like and subscribe for more cosmic discoveries.